Hey guys, this is Miss Gray, and we're doing AP Chemistry. It's kinetics time. Last time we learned how to write a differentiated rate law. This time we're going to look at the data from a slightly different perspective in the integrated rate law, and I think you will like the power that this gives us to do our calculations. So basically with the integrated rate law, our job is to figure out how to get a straight line on a graph. And really, it's pretty easy because you guys already know the equation of a straight line. Where's my writing utensil? There we go. Okay, so we have y equals mx plus b is the equation of a straight line. So if we can get a straight line, we'll know mathematically what to do. We put it into this format. So if we were looking at first order reactions, then we know our rate is equal to k times a to the first power. In order for us to get this to be a straight line on a graph, though, we'd have to plot not the concentration of A versus time, but the natural log of the concentration of A versus time. Let me show you what I mean. So here's my data that has time and concentration, all right? And I'm going to put this on a graph. So let's make a graph out of this. Get my iPad over here. So I'm going to put time on the x-axis, and we'll put the concentration of A on the y-axis. So what we see is a graph that's not a straight line. That's okay, because I know exactly what to do about this. Instead of graphing just the concentration versus time, let's graph the natural log of the concentration versus time. Now let's graph this, and let me show you what this graph looks like, because the whole point is for us to get a straight line graph. So again, I'm going to put time on my x-axis. Time is a good independent variable, because no matter what we do in the chemistry lab, time just keeps on going no matter what we do, so it doesn't depend on anything else. Hey, look at that graph. That looks way more straighter. So let's add a line, and we'll get the equation of our straight line printed right on there. That's not too bad for a straight line, but you know what? I don't think it's good enough. It's not as straight as I want it to be. So we have another route to take. Not only could there be first order reactions, but we know there could also be second order reactions. So let's give this a try. Go back to our data, and let's try the inverse of our concentration this time. So if I have the inverse, that means it's going to be 1 divided by the concentration. Let me type that in, concentration. And there we go. It's basically flipping it over, making it a fraction, right? So let's look at this data. On a graph, if I were to plot time on my x-axis and the inverse of my concentration on the y-axis, we want to get an actual straight line, a really straight line, not just kind of sort of straight. Let's see, how's that look? Now the last one looked straight to me, but this one looks even straighter. Let's put the equation of our straight line and see what it turns out to be. Wow, all of the points are lying along my line. That's a much better straight line than what we had before, don't you think? So what does this mean for us? If the equation of our straight line is the one with the natural log, then we know it's a first order rate, where the natural log of A is my label for my y-axis, and time was my label for the x-axis. Spelling can be a challenge sometimes, right? And then minus k becomes the slope. You know what? I think I already wrote all this stuff out for us, so let's just move on. There it is. Y equals mx plus b is the equation of our straight line, where the y term is the natural log of A. Time is my x term. K represents the slope of our line, but since we had a slope going down, a negative slope, let's look at that. That was this graph, right? We have a negative slope, then K is going to be equal to minus the slope of our line. Whoops, go back. So the slope is minus K, because it's going down. It's also easy to see what the half-life is, because if we know the slope of our line, then we know the value of k. Hey, now, go back. And if we know the value of k, then we can get the value of the half-life. So check it out. If I have 100% of my substance, then that means I'm starting with, let's say, 100, because A sub O represents my initial amount of stuff. And then at the half-life, that means I would have 50% of my substance. So far, so good? Now, when we're doing math with logs, subtracting the natural log means division, because we're dealing with exponents here. When you divide, you subtract the exponents, right? So basically, I've reduced 50 over 100 to be 1/2. Are we all okay with that? Since it's the half-life, that should make sense, right? All right, so in your calculators, I want you to take 1/2 and find its natural log. Do it now. Okay, fine, I'll do it too. Let me get my calculator. So we're going to find the natural log, ln, not log, ln, of 1/2, which we can also call 0.5. And I get negative 0.693147. So let's see what that does in our equation. Natural log of 1/2 is negative 0.693147, and that's equal to minus k times t at the half-life. So I'm going to call this t 1/2, the time of the half-life. So how do I solve for half-life? Divide both sides by minus k, and I get t 1/2 is equal to 0.693 over k. This should look really familiar to you from nuclear chemistry. Nuclear reactions follow first-order kinetics. And so that's why this equation is nothing new for us. So we know what happens with a first-order reaction. I showed you also a second-order reaction when we had Ka squared. That's the graph, to make it a straight line, of the inverse of the concentration of A. So let's look at that graph again. There we go. There's our graph of our straight line. And that one was straighter than straight. We're going to talk in just a little bit about what do we mean by a straight line and how straight does it have to be for us to call it straight. But this is the one where we had the inverse of the concentration of A versus time. So let's see what happens here. When I put this into y equals mx plus b form, then my y-axis has the inverse of the concentration. My slope is positive k. This one was negative k. And then time is my x-axis. And then this is my y-intercept, of course, because we always start our graph with the initial amount of the concentration of our stuff. And then it should decrease from there, right? So if we move the equation around again like we did before, we can figure out what the half-life should be by relating it to k, because we just read the slope from our graph and we get the value of k. Then it's easy to find the half-life. Now, a zero-order rate law means that the rate doesn't have anything to do with that substance. So we could write it this way, that the rate equals k times the concentration of A to the 0 power. But anything to the 0 power is just k, or is just 1. Yeah. Any number to the 0 power is equal to 1, so our rate is just k, not k times A to the anything. So we can express the concentration of A as decreasing with a slope that is equal to negative k, because I said concentration decreases, so our slope is negative, right? Concentration is going down, and so it's minus k because it's going down. In this graph, this slope is increasing. But when your slope is decreasing, then of course we just ignore that negative sign and put k as the absolute value of our slope. T1/2, again, we could rearrange the equation when we have half the amount of our substance and figure out how to get the half-life based on the value of K. So now that you've seen kind of the process, let's apply it. Let's do it for real. Here's an example, the integrated rate law. In example 3, we see for this gas phase decomposition, here's our reaction. NO2, nitrogen dioxide, is turning into nitrogen monoxide and oxygen. We want to write the rate law and determine the value of the rate law constant. So to write the rate law, we need to know what order of reaction this is. Well, lucky for you guys, the numbers that I put in my calculator are these numbers. I know. There we go. We plotted here the time in my x-axis. So in your calculator, I want this to go into list 1. All right, so type in the time into list 1. Then the concentration needs to go into list 2. If you don't remember how to get there, it was stat, then edit. All right? And then to find the natural log of the concentration, you're going to type in ln of L2. And that's usually in parentheses already for you. All right? And then to find the inverse concentration, you type in 1 divided by L2. It's important, too, that when you're typing these types of formulas, your cursor has to be on the place that says L3 or on the place that says L4. It can't be on the first line. It has to be on the top, on the header. And you can change the title of your headers, too, if you wanted to have time, concentration, and all of that. If you're using an Inspire calculator like what I'm showing on the screen, then you have to put in headings. Well, you don't have to. It just makes your life easier if you do. But on a TI-83 or an 84, it just says L1, L2, L3, and so on. So now that you've got the values entered in your calculator, how do we know if this is a straight line? This is the part where I told you I wanted to talk about how do we know if straight is straight enough. So you're going to push stat, then calc, and then we're going to do, on my calculator, it's choice number 4, len reg that says AX plus B. All right, so when I do that, I get a printout of all these values for A, B, C, D, and so on. No, not A, B, C, D, just A, B, and then R and R squared. The R squared value is the one that we're after. So for my concentration in of A, that stat, calc, len, reg, that line turned out to give me an R squared value of 0.927. For the natural log, for my list 3, that R squared value turned out to be 0.982. And the R squared value for the inverse concentration turned out to be 0.9997. So which one of these is the straightest? The one where R is closest to 1. So which one is it? Yep, this one's closest to 1, and this is my R squared value for the graph of my line of the inverse of the concentration of A. What does that mean? That means that this reaction from example 3 is second order. So it's second order with respect to the substance we were measuring, so with respect to NO2, which is our only reactant, so that's not really a big surprise, right? So rate equals K times the concentration of NO2, and it is second order, so it's raised to the second power. That's a lot easier than doing a differentiated rate law where you have to type in, 3 different experiments and compare one to the other and all of that nonsense. So we know this is a second order reaction. We know what the rate law is. Let's determine the value of K. So here's part A. Part B says to determine the value of K. K is going to be equal to the slope of this line. Was this an increasing slope? Yep, it's an increasing slope. So you don't have to do major calculations. If you're using a TI-84, you're looking at A equals. So I need 0.5431. Do I get to keep 4 sig figs? Look at your data. Now let's look at the units, okay? Rate is going to be molarity per second. and then we're looking for units of K. Concentration is molarity, and that one was squared. So K must have units of molarity over second over m squared. So one of my m's cancels out here. My units will be molarity to the first, seconds to the first. Now we've answered part A, and we've answered part B. So let's look at another example where we have the time and the concentration of a substance given to us from an experiment. When you're given experimental data with just one experiment and a list of times and concentrations, then that means we're going to use the integrated rate law. So our job is to determine whether the reaction is first order or second order. That's the first job. And then we'll figure out the value of the rate constant and the half-life from that. So let's put this into our calculator. So I had 0.1 moles. So I'm telling it to do the natural log of the concentration. So there's those values. When you do this, you'll type into your list 3 is going to be equal to the natural log of list 2. Then hit enter and all those values will copy down for you. Now I'm going to do the inverse of my concentration. So it's 1 divided by the concentration. And then that copies down all of those values. So for you, into your list 4, oops, sorry, I didn't know where my cursor was. We're going to take the inverse, so 1 divided by list 2, and hit enter, so it copies down all of those values. Now, because I'm using the Inspire calculator, I get to graph this and see what the graph looks like, so I'm going to do that. Let's graph time on the x-axis and the natural log to see, is this a straight line for a first order? Seeing that dot out of place makes me wonder if I typed this incorrectly. Did I miss something here? So let's go back to the graph, and that's not making a straight line, but it's kind of straight, all except for this point here that I can't really explain where that came from or what it's doing there. Let's look at the inverse and see if that one's any better. Let's see if a second order reaction does a straighter line. So there's my time, and here's the inverse of my concentration. And again, I have some goofy point kind of out there floating, so I can see, though, this is less straight. And to see what we mean by straight or by less straight, let's do stat calc. And I don't know how to do that on my Inspire, so we're just going to write it out here. So you're going to go to stat, then push calc, arrow across to calc, and I'm going to choose lin reg, which in my calculator is choice 4, and I need to tell it then to do list 1 for time and list 3 for the natural log. So if this were a first order reaction, then my r squared value would be, it's coming up as 0.9998. And if this were a second order reaction, then my r squared value comes up there as 0.94676. So it's not as good of a straight line. This data is giving us a better first order reaction than second order reaction. So we've answered the first part of the question. This is a first order reaction because that's the one that gave us the best straight line. So the value of the rate constant K is going to be minus the slope of my line. So let's go back to my straight line and print the equation of that line. Or in your Lin Reg, you're just looking at what's the value of A. For my calculator, I come up with a straight line. Let's see how it does compared to my other graphing calculator. So I got 0.008 for that slope. And then when I used my TI-84, I got a value of A to be 0.0101. So we're going to go with this because I didn't have this goofy point. I don't know what that guy's doing there, but it's throwing off my line. I have to see what I messed up. Maybe you guys will find it and tell me what I did. So the value of K is 0.101, right? No, I need a 0, 1, 0, 1. I get to keep 3 sig figs, and it's a first order reaction, so my units need to be seconds to the -1. And half-life in a first order reaction is 0.693 divided by K. So I'll put in there 0.0101, and that's per second. So I get a half-life of 68.6 seconds. There we go. So now we've handled all the questions from example 4 just by figuring out if it's first order or second order. That wasn't so bad. Let's try another problem. If we're using the integrated rate law, then half-life is a lot simpler. So the reaction of butyl chloride with water is a first order reaction. So that tells us something right there. The first order reaction is going to follow the kinetics using the natural log. So that's why plotting just concentration versus time does not give us a straight line. So the first question says, from the graph, estimate the half-life. And I put the lines in, so sketch the lines in on your graph, on your packet, so you can see what's the best fit here. And I estimated my half-life when I drew a straight line to be about 350 seconds. Now we can calculate the rate constant K because it's 0.693 divided by the half-life, 350 seconds, and that turns out to be, get your handy calculator out, 0.00198 seconds to the -1. Always be sure that you check the units for time on your graph or in your data just to see what those units are and make sure you put the right units down. Sometimes they like to put in minutes or hours just to mess with us, right? So always be careful. Let's do another example. Oh yeah, I put this in here to remind you of what half-life is. Since we did nuclear chemistry though, you know what half-life is. It's the time that it takes for the concentration of a reactant to drop 1/2 of its initial value. And that time is going to be constant no matter how much stuff you have. Here's another example of how we might be asked a question regarding kinetics. The decomposition of a certain insecticide in water follows first order kinetics with a rate constant of 1.45 per year at 12 degrees Celsius. So, assuming that the lake temperature is fairly constant throughout the year, we need to know what's the concentration of the insecticide on June 1st of the following year. Since this is first order kinetics, then there's some things that we can summarize about this reaction. So, since it's first order, that means that your rate law looks like this, K times your insecticide to the first power, but it also means the equation of our straight line is one where we use the natural log of our substance equals -K times T plus the natural log of the amount we started with. So there's the equation of a straight line for first order reaction. Our next step is to plug in the values that we know. So let's summarize what they told us in the problem. We are given the value of K is positive, sorry, not negative, 1.45 per second. And then the time that we're given to deal with is 1 year. What? Oh, okay, yeah. K is in years. Wow, I would have messed that up. But the time is 1 year, so that's going to be easy math. And then our initial concentration of insecticide released into that waterway was 5.0 times 10 to the negative 7 grams per cubic centimeter. And then we need to calculate the concentration of A. So we know everything in this problem except for the thing that we need to find out. So we'll take the natural log of substance A concentration is equal to negative 1.45 per year times the time of 1 year. There's our easy math. Plus the natural log of our initial amount, 5.0 times 10 to the minus 7 grams per cubic centimeter. So let's do this math. The natural log of the substance of A. The first piece is easy, right? Negative 1.45 years have canceled away. Plus, find the natural log of 5 times 10 to the minus 7. I got negative 14.50866 grams per cubic centimeter. So since I'm adding two negative numbers together, we find the sum. When they have the same sign, we find the sum, not the difference. So it's negative 15.96 grams per cubic centimeter, rounding. And how do I undo the natural log? To undo log log, we use 10x, but to undo natural log, we use e raised to the power of this, just gives us a, because e is the inverse of natural log. So then I need to take e raised to the power of negative 15.96, and I get 1.73 something something times 10 to the minus 7. Well, how many sig figs do we get to keep? Looks like we started with 2, so let's call this 1.8 times 10 to the minus 7 grams per cubic centimeter is the amount of insecticide left in that waterway after a time of 1 year. So we use the equation of the straight line to solve problems about the reaction with first order kinetics. Now let's answer part B. This was the answer to part A. What's part B asking us to do? Let me go back and check. How long will it take for the concentration of the insecticide to drop to the EPA acceptable level of 3 times 10 to the minus 7 grams per cubic centimeter? I don't need that. I need a white screen back. Okay, so now we have to calculate time because it says how long will it take? We need to get to 3 times 10 to the minus 7 grams per cubic centimeter when we started with 5 times 10 to the minus 7 grams per cubic centimeter. So we're calculating time here. Here's my unknown. That's what we're trying to solve for. So when I'm subtracting the natural log across, remember what we do? That's like division. So I'm going to put the natural log of 3 over 5 is equal to negative 1.45 times time. So let's divide both sides by negative 1.45. And then we'll apply our calculator so we can get the value of time. And my handy dandy calculator gave me 0.35 years. So that is a little over 4 months for that insecticide to decompose to a safe level. So use the equation of your straight line in order to determine the answers in kinetics problems. We have one more example, I believe, or two more examples. A certain first order reaction is 23% complete in 42 seconds. Determine the rate constant and half-life for this process. Sorry, I got Dropbox stuff popping up. So let's write our first order reaction. Because it's first order, we're going to use the natural log. not inverse or just concentration. So here's my equation of a straight line. And when I subtract the natural logs across, then I get natural log of concentration of A, my part that's left, divided by the concentration of my initial amount. That was my whole. So when we're doing percent, this is pretty straightforward. The problem is you have to reread the question. If it says it's 23% complete, then how much of my stuff remains? It's 100 minus 23, right? So I have 77% remaining out of the 100% of stuff that I started with. And then my time in this problem is 42 seconds. So I'm going to put that in here for the time. Let's divide both sides by 42 seconds. So I can solve for k. So I'm going to get negative k is, get your calculators and apply this math. Negative k is equal to negative 0.00622, and so k is just 0.00622 per second, because our time was in units of seconds. Now it says determine the half-life. Well, since it's first order, this is easy. Half-life is 0.693 over k, so that's 0.693 divided by 0.00622, and I get a time of 111 seconds. Let's keep going. We have one more example to work through. In this second order reaction, it's 67% complete in 27.3 seconds. So a second order reaction has 1 over the concentration of A equals K times T plus 1 over my initial concentration of A. There's the equation of our straight line. So next, we're going to put in the numbers we have. So if it's 67% complete, how much of it remains? 33. So I have 1 over 33% equals K times 27.3 seconds plus my starting amount we're going to call 100%. Does that make sense? We started with all of it. We went in the reaction till only 33% was remaining. So now I'm going to move things across. I have 1 over 33 minus 1 over 100 divided by 27.3 seconds. So let me show you the keystrokes that I use in my calculator to get this accomplished. Okay, so what I want to do is take the inverse of 33. So I type in 33 and then I just push x to the minus 1 on my calculator. And then that number is going to subtract 100 to the minus 1. And then finally I want to divide the whole thing by my time, 27.3 seconds. So my rate law turns out to be my rate law constant turns out to be 0.000744. K equals 0.000744 per second. And then the half-life is going to be 0.693 over K. So I take 0.693 divided by my answer. And I get 931.452. How many sig figs? 3 sig figs? Yep, looks like 3 sig figs. So Let's just call that 931 seconds. There you go. That's how we use the integrated rate law, not just to determine the rate law for any reaction, but also to answer follow-up questions about those reactions themselves. So we'll practice this more in class, and I'll see you soon.